a nice little crowd here. So yes, I'm going to talk to you guys about 3D geocellular model, but mostly what I want to talk about in that is how practical that approach is, especially to mature fields. So a lot of us work in areas with a lot of old oil fields, a lot of old wells. So how can using a new technology help us to understand and milk a little more profit out of some of the older areas? So that's the overall theme. And so in overview, what I'm going to talk about is, so I'll give you a little bit of background. What is a 3D geocellular modeling and why is it useful in mature areas? And, you know, how is it different than the conventional methods that we typically use? And what are the myriad of different things we can use it for? And for most of this, I'm just going to show you some examples of some real oil fields that I've worked up in the past in Oklahoma and maybe also in Texas, time permitting. So that's the idea. So why would I want to do this talk? Well, okay, I mean, geophysicists work in 3D all the time, but us geos often are limited to working in 2 dimensions, either map plane or cross section. And 3D geocellular modeling, so the ability to work in 3 dimensions, it's not really new. The software has been around for, I don't know, maybe 15, maybe 20 years. Okay, so it's not really new, but what's really happened, sort of snuck up on everybody, is that the elements that make a 3-dimensional model work and make it practical have only recently appeared together. So we've had certain elements that would appear at different times, but getting everything together to make it work is pretty recent. So, you know, I built geocellular models maybe starting as much as 30 years ago in the country of Algeria. Worked for those guys for about 15 years or so. So, you know, I worked in some world-class fields there. I've done basin-wide fields in the United States, things like the Marcellus in Pennsylvania, and dozens of little small mature fields. Yet, when I go in and I talk to, you know, particularly smaller operating companies or geos just in general, you know, I talk about modeling, and a lot of people just don't have any idea what I'm talking about. What do you mean by that? And so, you know, I think there's a tremendous amount of benefit that can be gained by doing 3D modeling, and it's really become practical, and it's especially applicable in some of the older areas. So that kind of lays the groundwork for what I'll be talking about all along the way. So some things to think about as we go through this, okay, is that, you know, geomodeling is practical. I say even for small operators. So I've done projects, you know, for guys that only have small fields left and right, and they've gotten a lot of benefit out of it. One of the cool things that geomodeling can do is it can take, if you've got it, vast amounts of information and get it all in one place so you can come up with new ideas about what's going on in the subsurface. Okay, and another important, and in fact, for that, it's like, in case there is so much information that it's really hard for you to interpret as an individual. So gives you a new idea for that, and it uses your existing data. So it's not like you have to go outside and buy a bunch of information left and right to get this stuff to work. You can use, most of the time, the information you've got. Maybe you already have it. You're just going to be using that information in a different way. And so you can combine different types of data, let's say like structure with permeability, with porosity, and different things like that. Seismic, all of that can be combined into one space. And in doing so, you'll sharpen your geologic interpretation. So especially in older reservoirs, it really helps to identify where the reserves are or were, okay, and where those reserves could be hiding today. And you can use this both for primary, so drilling new wells, and I think it's especially helpful if you're doing secondary recovery processes. Okay, so, and it's really nice for horizontal well plays because I mean, in addition to all the geologic factors, you've got your wells that are at different depths, staying in the zone, out of the zone, all that kind of stuff that you have to try to contend with. And that's really hard to do in a two-dimensional plane. And another thing that I really love about it is that it really strengthens cross-disciplinary collaboration. So geology and engineering can work together in ways that you couldn't work before. So, and then finally, it makes really powerful presentations for management, or if you're trying to get money to do a deal, that kind of stuff. It makes things really apparent to people that make those decisions. So, just very briefly, what is a geomodel? I'm going to zoom in on this little video that's playing in the corner just a minute. But anyway, so a geomodel is a virtual reservoir. And so that means everything becomes 3 dimensions. So everything, your tops, your surface data, seismic data, perforation, well logs, cores, everything, all of that information gets consolidated into one place where you get an idea as to what's happening universally inside your field. So this stuff has been used for quite a while by major oil companies, but now prices have dropped and data is available so that this type of work can be done even for smaller oil companies. So, and at one time, the only reason that people would tend to do this sort of thing is because modeling in 3D was a stepping stone to get you to modeling geology. A static model of geology is a stepping stone to get you to a dynamic simulation where you're trying to predict the flow and movement of fluids inside the reservoir. Okay, but my opinion is that the best benefit to doing 3-dimensional geocellular modeling is in helping you figure out how to develop a field and where you might have missed things and where to target your wells and that sort of stuff. So the day-to-day, starting from ground zero, is a way to go. So and then here's this little field. So this is Hassi HTF field in Algeria. So relatively small field, probably 5 miles by 3 miles in size. Okay, so this is an actual model that I made for those guys. So, we're coming in, and in this case, I have one layer of not so good seismic that helped me to establish the top of the system and where the faults are. Okay, and then all the rest of the information, structure tops, everything else is coming from the actual well bores. So you see the well bores, there's the surface, you can see the faults that are in there. So this stuff is built into that model. So obviously structure, so you can pick it up and look at it and rotate that around and take a look at, what your structure looks like from place to place. That big pimple in the middle there, by the way, is magmatic intrusion. It's pushed up the rocks in that particular spot. And so the cool thing about geology, about doing 3D modeling as opposed to doing the standard type stuff, is that you actually create a 3-dimensional volume of the reservoir. Okay, so we're used to looking at maps and isopachs and things like that, but when you're doing the modeling approach, you're taking your information and turning it into a 3-dimensional object where everything is spatially located as well as the properties that are contained therein. So what you're looking at right here is now a 3-dimensional volume of permeability that was made from logs and full hole cores that came from this particular site. You can also see, if you look at it, there are the wells, and there's these little yellow vertical things inside. So those are the perforations or the open intervals of the wells. So you get to understand how wells are perforated or open relative to the type of rock. So that, as I say, that's permeability. Kind of get that a little further along. So now what I've done is I've turned off the volume, and I'm just looking at the bottom surface of that reservoir. And you can see down that blue that's across there is the oil-water contact. Okay, so you can instantly see which wells are above the oil-water contact and which wells are below the oil-water contact. And then since we made a 3-dimensional volume, we can now slice that in any direction. Okay, so this is just an arbitrary slice going through the system. And again, this is permeability. I'm sorry, there's not a scale, but basically, The blue stuff is going to be around 1 millidarcy, and the red stuff is going to be around 10 millidarcies, so color-coded, okay? And there you go. So now you can figure out how to fully develop this particular field. And so I mentioned this before. So 3D geocellular modeling requires 4 main elements, okay? The physical elements that it requires, first thing is digital data, okay? So if you have a log, and maybe it is a raster log or even a paper log, okay, it is now affordable to turn that into digital information, okay? Just like everything else, you know, stock market, anything else, if the information can be in digital form, you can do things with it that you can't otherwise. So then the next thing is software. Software has really come a huge way. Originally, this type of software was only able to run on a mainframe, okay, or a Unix system. And today, you know, even a mediocre laptop computer, this one that I've got here, for example, can run these models and show what's going on, okay? And the PC power is the other thing, so the computers themselves have evolved and evolved so that now they're just incredibly powerful. So you combine all 3 of those elements, you've got everything you need to make a 3-dimensional model. But the last element is a skilled geologist. So this can be the, you know, take all of your geologic knowledge that you've had, structure, sedimentology, whatever, okay, those skills all come into play, and then you have to learn this software. All right, there it is. So that might be a little daunting, but it's certainly overcomable. So, and with combining all these elements, you wind up with a 3-dimensional model at the end of the day, okay? So why would you want to do this, particularly in old areas? Aren't they old and tired? And, you know, well, I mean, one good thing about it is that the old fields are rich in well density. So you got a whole bunch of information that can be useful for doing a 3-dimensional model. And then it's now practical to turn the logs into digital information. And you work in areas, maybe they've been plowed through time and time again, generations after generations of geologists have come in and looked at the same area, you know, and surely it's all gone. But most of the time that I've come in and worked on these older fields, you wind up with a surprisingly large amount of undeveloped resources that are just sitting there. And in large parts, you know, all the big majors and everything have moved off to the deep basins drilling horizontals. And so these older areas that had vertical wells in it are just laying there. And there's a lot of oil that is in these old fields if you can figure out the best way to get it out economically, okay? And by saying that, combining the data properly, you can reduce your risk of going into a field. I mean, in most cases, if you fail, your wells are still going to pay themselves out. And if you're right, then you're going to make a bunch of money off of it. So those are good odds across the board. So, and yeah, another thing is that, you know, what we're doing today is we have moved from great reservoirs all the way down to things that you would not really even call a reservoir. Okay, so the quality scale has gone down. And again, those are the things where you may have had dozens of wells going down for a deeper target, conventional targets, and now you've got the zones that are uphole that were too trashy to be dealt with in the past, which are today possible targets for exploitation. So one of the things I'll mention is about data accessibility. So I live in the middle of the Arbuckle Mountains, about a half mile north of Turner Falls. So I'm out there, okay? And even me working there, I can now reach out through the internet and grab information that's out there in various types of formats, digital or raster type formats. I can get that information, I can get my arms around it, and in rapid sequence, I can turn that into a 3-dimensional model. So, you know, I just pulled this little map here out of Inverus, see all the wells that are in there. Okay, I can take that information out, do a data dump from them, you're going to get something in a sort of a text file, and you can dump that information into a three-dimensional model. And you go from that flat map with tops on it into something where you see the wells with their depths and where they start at the surface, and if there's horizontals, what they look like, all that type of information. So the data is there. It's just a way of getting it in and viewing it. Next, well information. So, you don't have to have seismic to do this stuff. In fact, some of the best projects I've done are only using well information. So you've got so many old wells that are sitting there, the data density is so high that you can turn electric logs into something that really, at the end, the volume looks a lot like seismic. And at the end of the day, you can actually get more information out of the geocellular model than you could get if you only had seismic. So, and of course, if you got both, of course, use it, right? But today, for a long time, we were out going to the log libraries. My mouse is showing there. Good. All right. Yeah, so you go to the log libraries and you get some sort of log out of it. You correlate the paper logs. Today, you can relatively inexpensively take those paper logs and have those digitized into a digital file, which is the last file. And more the data services are doing that for you. So, old wells are systematically being digitized into last files that you can then take those last files and dump those straight into the three-dimensional model. So if you're looking like this was an actual well, here's the data. It was converted into a last file, and then it was dropped into the three-dimensional model. And so now you're able to do this type of representation where you've got a gamma ray resistivity, density porosity, neutron porosity, hydrocarbon saturation, plus whatever other curves you just want to display. Okay, and so then those guys get dropped into, for each well, now into the three-dimensional model. So you've got, for example, here now, this is the same well in the three-dimensional model, and now there's the structure that was generated for it. And you can see in 3 dimensions the gamma ray, basically, for that particular well. Okay, so you get that type of stuff, and the cost of doing that is pretty low these days. So the cheapest I've found is like $15 a curve to take raster information and convert that to digital. So now we're just going to go into looking at, here's some examples of fields that I've done in the past. So, this particular little field is coming from around Seminole. And this is the old geology that was done in the field. I'm not criticizing that. It was good work. But this is what you would typically get. So you get a structure map. You get an isopac map of something. Okay, could be thickness, maybe average porosity, whatever, right? And then you get a cross section. Okay, so there are limitations to this. Obviously, it's much more simple to see a three-dimensional object with structure than it is to look at a map and try to figure out what that's telling you. So it's more intuitive in 3D. Okay, but when you think about it, when you're like making an isopac, you're trying to describe the physical properties of that reservoir. So what would you do? So I want to know, here's my pay zone, and I want to make an isopac map of the net feet of pay, okay? Or let's say porosity greater than 8%. And so what I have to do then is I have to go in log by log. Sometimes there's software that can help you with that, but basically I'm going to go in and I'm going to find every foot in that sequence that exceeds that threshold, okay? Or I'm going to do an average. So I want to know what the average porosity is. So I go in, add all the data up, divide it, and get an average, okay? What I'm doing though is I may be taking 100 feet of log information that may have been put out in every half-foot increment, okay? And I'm taking, 200 data points, and for the purposes of having something that I can contour, I'm going to average all of those 200 points together to get one value that I can put on a map, and then I can draw contours with it, okay? And so you have grossly eliminated a vast amount of information just so that you can work from a three-dimensional object, just so that you can work in a two-dimensional plane, okay? Whereas with geomodeling, you don't really do that. So your data exists in 3 dimensions, and the volume is created from all that information in 3 dimensions. So, and many times it's just faster. So a lot of these hand calculations that we do are very laborious. And that sort of thing could be picked up very quickly by looking at, by incorporating it into a 3-dimensional model. Okay, so here's an example of that field. So the maps that you just saw now are now represented here. It's the same information that went into those maps, but now that information's been turned into digital information and put into a 3-dimensional context. So just like if you're doing a regular mapping exercise, you come in, you define your area. So the squares in here are 1 square mile. Okay, so you come in, you identify the leases, you get all that stuff in there. So now you come in and you take, it's giving me a little trouble here. There we go. So now, you know, I take the wells and I bring them in. Okay, but that well information is actually in 3 dimensions. Okay, so the surface, downhole, everything is captured in 3 dimensions. And then I'm appending to that the log data. So this is oil saturation being shown as a log. But just like what you do, so you go in, you make cross sections, and from those cross sections, you would pick your formation tops. So all those little discs that are being represented here are different formation tops that have just been picked in the standard manner. Okay, and then you will come in and I allow the software with my control to create the 3-dimensional surfaces. So here's all the different surfaces that tops were pulled for, Wilcox, all the way up to the top of the Woodford. Okay, so that makes sense. And we've all done this like a layer at a time. Here you build your layers and they're all represented at one time. In this area, I think there is 1 fault, so put in a fault. And then the difference is that now I have all those surfaces. What I'm going to do is to take those 2D surfaces and convert that into a 3-dimensional volume. Okay, so now I've told it to create that volume and split it up into the different formations. So now there's a volume in there for Woodford, Bodark, Harrigan, Henry House, you know, Sylvan, Viola. Each one of those different layers represents a different formation. And I'm going to divide that unit up into several million individual cells. So maybe in the XY plane, maybe a couple of 100 feet. And then in the Z plane, I like to stay around 2 feet. Okay, is like kind of a typical thickness for each of the cells. So this particular model has about 15 million cells in it. Okay, and so as I mentioned before, we have all this log data that's in that file. And so what I'm going to do is, again, mathematically, I'll work with the software so that I'm going to use all of the information from every well at one time to integrate into a 3-dimensional volume. Okay, and so this is hydrocarbon saturation. So this got a scale on it on the left over there. So 0 is blue, 1 is 100. Okay, and so now you see the different colorization. The gray just means I didn't model it, Sylvan. So, you know, there you go. So now that volume has been created in 3-dimensional space. So now once I have that volume, I can start doing cool stuff with it. So for example, I can come in and now create cross sections any direction I want to. I can go from well to well, north, south, east, west, doesn't matter. Slice this stuff up and look at it from any angle. So in this particular field, by the way, it's an up-dip erosional pinch out. It had previously been identified as being a fault structure, but in this case, the Acadian unconformity base of Woodford has eroded the top of the Bodark, and you have these erosional remnants that are in an up-dip position, and that's the actual trapping mechanism. So those two fields are represented here, one on the left, one on the right, as individual residual erosional features with a valley that was eroded through the center. Okay, splitting it up into two separate fields. So again, here you're looking at hydrocarbon saturation. I just picked that as a unit. So you can see where the streaks are, and mostly, obviously, the places that have the high hydrocarbon saturation are going to be high porosity type things as well. Okay, so now I can pull that through the model, look at it in different directions. And of course, now I'm going down in the dip direction. And so you can see the up dip erosional pinch out where the boat arc member is coming up dip, and then it gets eroded off to zero. There's a little valley, and then it actually picks up on a little bit on the other side of that. Okay, but that's the up dip erosional pinch out. Okay, so now I've got all the different properties modeled. So every property that you would typically use is in the model. So porosity's in there, permeability, well, porosity's in there, resistivity's in there, gamma ray, all that kind of stuff. And so I can do calculations, for example, for water saturation. But in this case, where I jump to that, so we actually have porosity now distributed in three-dimensional space. So again, the scale on the left over there goes from 0 to 20. And in this case, they actually had a core, and the correlation between porosity on the X scale and core permeability on the Y scale was pretty good here. There's one outlier point. It was kind of off in space. But generally, it follows something that I can then get an equation for. So I have an equation that can transform porosity into permeability. Okay, no magic there. I just then am capable of taking that equation and using that for the entire volume. Okay, so now I can take all the porosity in 3 dimensions and just mathematically convert it into permeability. Okay, and so now I've got permeability in millidarcies. It doesn't get up to 500, but it does get up to like 25 or 30 in places, so it's pretty good perm. Okay, and now you can see where the permeability is distributed inside the system. So this is now a map of hydrocarbon pore volume. Okay, so that is simply the 3-dimensional model of porosity, which is multiplied by the 3-dimensional model of hydrocarbon saturation. Okay, so that's giving you the percent volume of hydrocarbon inside the reservoir. Okay, and it's giving you that in a 3-dimensional manner. Okay, so one of the cool things that I can do then, so I have a 3-dimensional volume, but if I want to look at individual things in map view, I can do that. So I've already created, as I showed, like structure maps. So typically there's a structure map for the base of the boat arc formation. And then it's already in the model. I can tell it, well, tell me how thick the boat arc formation is. Okay, and so in this case, it gets up to a maximum of around 130 feet thick to the northwest. And as you go to the southeast, you approach an erosional up-dip limit. Okay, and so it goes to 0 where the boat arc is completely eroded. Okay, and again, that creates that up-dip stratigraphic pinch out. So my mind, I didn't have to really interpret this. The information, the data that was in the system gave me that interpretation back out, and it makes sense. So that's cool. Okay, but now I've got a volume in there, and I've got hydrocarbon pore volume. So, I mean, obviously, another thing we can do with that then is to calculate transmissibility. So that's the thickness of the reservoir multiplied times the permeability. So again, that's, now tells you how many feet of permeability that you have in the system. Okay, and then as we roll along then, as I mentioned, we have hydrocarbon pore volume, and you can tell the software to add everything up and tell me what the total pore volume is in the system. And so I've scaled this, you could use acre feet if you wanted to, but I prefer to have this reconverted into barrels per acre. Okay, that way it becomes very easy. I got 10 acres, barrels per acre. I can do the math pretty easily and come up with the original oil in place, et cetera, et cetera. Okay, so that's what I did here. So, how much oil is there in the system? So, again, now I've come in and done the math. Move that forward just a little bit. So the model tells me now out of these two features, I did them individually, but collectively, there's 54 million barrels original stock tank oil in place. Okay, but the actual cume that has been produced is about 3 million barrels. Okay, and so pretty quickly then you can look at it and say, my recovery factor for this field is only about 5%. Okay, so according to me, there ought to be a lot of oil left over in this feature. And previously, there were just little stripper wells out here, a barrel and a half, that sort of stuff. So the operator, just because the wells were handy, came in and he set up one of the wells here. I didn't put the decline curve in it, unfortunately. But he set up an injector in one of the two fields. So, and then had one well that was producing out of that. And that producer went from like a barrel or two per day up to 150 barrels a day within a few weeks after he started to do the injection. And so the decline curve for this well gives him about 383 million barrels. 1,000 barrels that he'll be able to produce out of this well. So what's his efficiency on that? So you can establish a radius of drainage for the well. And then if you look at that, you say, all right, now again in the model, under a reasonable drainage area, how much oil is there in place? So the model says, okay, for that area, there's 1.1, almost 1.2 million barrels. So we're going to produce 383 out of it. So that's telling us then that he has approximately a 32% sweep efficiency, which is pretty good. Okay, and so if he can do this across the rest of the field, he's going to turn stripper wells into 16.5 million barrels. Okay, so it's a good example. He's done some other development in the area, which is validating the point. And so here's another one. This one is coming from, yes, sir.
Originally, though, it had EUR per well 30,000.
I'm sorry, I didn't quite catch it.
What was the original EUR per well in that last example?
Oh, I didn't do it per well. It was just for that one well. Okay, yeah. I'm not sure if I can get back to there. Yeah, no, that was no, I didn't put what they had before they flooded in there. Yeah, so it's just for these two. So the injector there, a pattern of capture by the producer. Okay, and then under that capture area, there's 1.1 million barrels of original oil. This one? Yeah, this one? Yeah, so I'm sorry, yeah, so not by well, but for the entire field. Yeah, for the entire field, they got 3 million out of it. Yeah. But anyway, this is actually fairly easy to do. So once you get the data in digital form, even some rough approximations, you can get a pretty good idea as to what the original oil was. And if you can get good production records, you can see how much was produced, and then look at it like field by field and say, wow, there should be a lot of oil left over here. Why don't I go and see if we can get that out? So here's another example. This is a bit newer. So this is coming from the Ardmore Basin. So just like before, the operator here has got a couple of fields. We're mostly just going to look at the field to the south. I define the project area. I'm adding the wells. Those are just coming from Inverus. Okay, so now the wells are in the feature. And we digitized the logs and put those logs into the individual wells. Okay, I went in and picked a gazillion tops for this thing. And by the way, so let's say, like you want to use this technique on something, you already have tops picked. Cool. That information can just be sucked right in and used immediately. So I picked a lot of tops here because there's some faulting, and we wanted to make sure and catch if there's any faulting that's up dip a little bit. So again, picking tops. And in this case, there was a reverse fault located in the area there. So that's what the purple bubbles are all the locations in the wells where we found this reverse fault. Okay, so you're looking at this now from the side, from the south looking towards the north. Okay, so the model created basically a fault plane for me. So there's the actual structure on that plane, so you could figure out where it's at. Okay, now I have my formation top. So again, I'm going in layer by layer. So mostly this is in the fusilinid formation. So it goes like from top of Tussey up through lower, middle, upper fusilinid. And then I add to that the actual fault that was in there. I'm just playing around now so you can see through the fault or what the underlying structure looks like. Okay, we convert, so this is only looking now at the lower fusilinid. So split it up into its individual formations like we did before, divide that up into a bunch of little cells. And so now here are the kind of results. So now we're looking at it on the top of the Tussey, which is the bottom of the producing formation here. So you can see that big gash on the side here. That's where the reverse fault is cutting through at that particular layer. Okay, and so again, now I've added the oil water contact so you can see explicitly where the water is, and I need to stay above that. Okay, and then I didn't show all the volumes and everything here, but this is now hydrocarbon pore volume. And I just made one slice. So there's a whole bunch of individual properties that are in this, all the porosity and everything else is all in it. But this is now just looking at the porosity multiplied times hydrocarbon saturation. So you see kind of like, all right, where's the oil at? And again, obviously, more hydrocarbon saturation is in the zones that will have higher porosity, okay? So now he had a series of wells out here, and if you look very closely, you can see that little kind of an orange yellow looking stripe on the wells. That's the actual perforation. That's great, but if you really start taking a look at it, what you can see, I'm sorry, I should have done this. Now, stop. Yeah, there we go, good. So if you start to take a look at it, so there's a porous interval that's rushing, back up a second, there we go. All right, so there's a oil-bearing layer that comes up like this, and this well is perforated in it, okay? But then there's a step down, and there's another oil layer that comes across, and this well is perforated in it, okay? And then there's another layer that comes in, and that well is perforated in it, and you got to look around the corner, but you see now there's another layer coming in with a different well that's perforated in it. So
we have a question online, and I think everyone has it. What software are you using?
Oh, yeah. So I am using software made by Baker Hughes. Okay, which is called Joule.
Okay.
Joule, and I'm happy to answer any questions on anytime anybody wants to email me or something. So be happy to give you the info on it. So anyway, okay, there's all the different zones. So what the operator was looking at, it's all called the same thing. It's all called the X sand, right? And he was trying to inject, but he wasn't having any success. He wasn't getting any production for his injection, okay? So a cool thing then is, so I come in, and this time what I'm doing is I'm taking lens by lens, okay? So there is his upper lens. And so for that upper lens, I have calculated barrels of oil per acre. So now you look at it as a map. And so this bottom horizon is at the bottom of that sand lens. And the oil that's being shown is the oil that comes out of that sand lens being projected in its true structure, but now the volume, the amount of oil that's in that lens can be seen at the same time as you look at the cross section where you can see its position in three-dimensional space, okay? So there's the first lens. And then if we look, we can get to the second lens, the third lens, fourth lens, and the fifth lens, okay? And so again, out of this field, various reservoir volumes, but basically of the main formations that are in there, there's like 6 million barrels and, 6 million barrels. But his primary production out of those 6 barrels has only been about 8%. Okay, and so there's, again, plenty of room to be able to get more oil out. But what he looked at it and goes, well, that explains why I don't have production coming out of my wells. My injectors and my producers aren't in the same lens. Okay, so now he can go back in, put his injectors in, his producers in, and get them all where they're working together to get the oil out of the ground. And I will just do this extremely fast. So, so this is now looking at that formation, the Wolfcamp formation in Howard County, Texas. So there we go. There's a whole county, about 40 miles wide. This was a set of vertical wells that existed before the horizontals were drilled. Pick the formation tops. Okay, and now all I've done here is distribute the gamma ray in 3 dimensions from the model. And I've got it color coded. So the blue is the limestone. I'm gonna back that up just a scooch right here. Okay, so the blue is limestone. The kind of gray stuff is just like regular shale. And the red is hot shale. Okay, so there we go. And look, I mean, look at the stratigraphic complexity that's in this system. I mean, if you came in here and tried to do this by hand, you know, going from well to well, what's my pay zone, that kind of thing, trying to figure this out, it'd be tough, you know. But again, the information goes in, you tell it how you want it to work, and that information comes back out. So now I can take a cross section, you know, and I'm just going to scroll it across there. You can see how the different facies are distributed in 3-dimensional space. So that's a Wolfcamp A, B, C, D in there. Okay, and then you can begin to look at, okay, well, where are the operators drilling their wells? Okay, and how are they doing? So same thing. Now this is hydrocarbon pore volume, just like before. So, you know, high amounts of pore volume are the brighter colors. So look at how that's distributed. I mean, you can get something good or you can get something so-so. And again, now we're looking at it just from the top. So I'm going to look at the Wolfcamp A here. That's that upper layer just below the 2. So now I put the bottom of the Wolfcamp A, so that's Wolfcamp B we're looking at here. Okay, and now I sucked all the oil out of it and turned it into a map. So that's millions of barrels per square mile in this case. It's like up to 180 million barrels a square mile. Pretty good. Okay, so where is it? And now I can scroll through that and see not only where is all the oil, but how is that oil distributed in the vertical plane, which might influence where you want to drill your wells for fracking. So anyway, that's that. And the conclusions, which I think are fairly evident along the way. So anyway, all of our data now is at a point where, you know, it's really practical and cost effective to do this type of modeling. And I'm sure the geology is going to move to 3D routinely. I mean, eventually this is where geology's got to go. Okay. And where a lot of us are working in mature fields, got lots of data. This is perfect for modeling. And, you know, I've seen in what I've done lots of opportunities in old areas, which are, you know, basically maybe poor quality reservoirs, but we can exploit this with new technology. We can find a lot of bypassed oil. We can figure out how to optimize secondary recovery. So, you know, the cost of doing this sort of thing versus the benefits that you get out of it is way one-sided. So that's it. And thank you. I know this was a little bit long, but I'm long-winded. Thank you. And I'll take questions, but if people have to go, that's cool. So.
Anybody else have a question?
Does the, you know, like on this, that smaller structure?
Yes.
Obviously, they didn't have 3D before, right?
Oh, no. Yeah.
Shoot or something.
No, well, there's no 3D on that first one. Yeah, there's no seismic involved in that one at all. So those are basically well tops.
Okay, all that was done just off the well top.
Exactly.
Okay.
Yep. And most of the time, that's what you get to work with. So, but as I say, if you have seismic, it makes it even better. So, yeah, absolutely. Yes, sir.
Yes, in every way you have, say, 3D seismic, and you also have your well control. How do you handle when you have discrepancy in your well, I mean, like your picks relating to the seismic events? You just kind of use your seismic as survey trend, or?
I'm sorry, but seismic is perfect. I can't imagine. No, I'm just kidding. So, yeah, I mean, honestly, you know, I mean, a secret that doesn't get out so much, you know, is that most of the time when you're converting seismic from time to depth, you're using well tops. Okay. I mean, that's what, so like traditionally under the covers, the way that's often done is you're going to have multiple wells that are out there. You've got a time surface. Okay. And you've got picks for that. Okay. And so with a pick and time, you can, you know, you're going to get the seconds transit time. Okay. So you get that, you get your velocity, you know, out of those wells. Okay. And if you, for our purposes, then if you just get the time surface, okay, so instead of the converted to depth, so that's where you can, so you got an estimated depth surface from seismic and you got a well point and they don't match, okay. To get around that, the best way to do is get a time surface, okay, and then you're going to use all of the wells that have tops in the area to give you a velocity map, which will then convert the time to depth, and there won't be any discrepancies between the two. All the data will match. Yeah, it's just not that hard. And a lot of, I mean, geophysicists, many of them will do that, but they may not have all the wells in there.
And I guess you're assuming that you have ample shot surveys or velocity surveys.
Right.
You can do something.
Yeah, I mean, your well tops become check shots. I mean, you know, every well that's in there, you know, you've got now the seismic time to that horizon and you've got the absolute depth. Okay, so you can create a velocity map that's using, you know, all of your tops data. And so the resulting structure will match reality for the tops. Now, there are other ways of handling that. So let's say if you only had a structure map, okay, that's what you got from seismic. Okay, then there are ways of going in, for example, doing what's called co-trigging. And so for co-trigging, it's a technique where you have your hard data formation tops, and then your seismic becomes soft data. So it gives you sort of the trend as to the way things are going, right? And the software will work with both data sets. So it will match your observed tops. And where you have observed tops, then as you are trying to estimate points, as you come into those observed tops, it's going to start to match the observed tops. But when you get away from your real tops, so that all you have is seismic, then it will blend the seismic depth into that.
And I understand that the amount of hydrocarbons in a well with the seismic around it, that your seismic will be different from, say, a well that has a lot of gas in it versus one that's, basically has no gas.
I'm sorry, say it again, one more time, please.
Does the amount of hydrocarbons, especially gas in a well, that is going to be another monkey wrench in your seismic?
I mean, the depth maybe not, but amplitude, may be affected by that. So actually a cool technique that I've used in gassier areas is that you can go in and calculate your gas expansion factor in a three-dimensional manner. And so, as you're getting deeper, your gas is getting more compressed, temperature's changing, all that kind of stuff, right? And yet your original hydrocarbon pore volume is the same. Okay, what's different is that if it's gas, so you've got a pore volume, but that pore volume now, as it comes up to the surface, is going to expand and change volumes as you measure it. And so you can create a three-dimensional gas expansion factor, okay, and then calculate your hydrocarbon in place. Okay, you can get an original hydrocarbon in place map, and then and that would be at reservoir conditions. Okay, but then as that comes to the surface, it will generate another volume, another map, which would be the produced gas in MCF. And we did a lot of that in the Marcellus up in Pennsylvania. It worked really well. It's pretty cool. There's even a technique that I worked on up there, which estimates really nicely pore pressure in unconventional reservoirs. And we applied that up there and got, in fact, not only in that formation, but Utica and Haynesville and a few other places where you can estimate the amount of hydrocarbon the pore pressure in situ before you drill even. It's a pretty cool technique. Yes, sir.
I was curious how you use a gridding algorithm to do this operation, because there isn't just one, there's a variety of different gridding methods, and it's going to affect the output. You're going to get different numbers from different grids. So what decision process do you go through up front to say, we're going to use inverse distance weighting, or we're going to use spline, or we're going to use triangle? How do you make that determination?
Yeah, so I will use kriging always 100%. Okay, because the other techniques you just mentioned have some really serious mathematical flaws in them.
Kriging is more probabilistic.
It is. Plus, so it's like well, here's a good way to understand it. So imagine if I have two wells, one has 0% porosity, maybe 0 and 10. Okay, and I want to get an estimate of what the value is in the middle. Okay, so you'd look at that and say 5. Okay, 0 this side, 10 on that side, 5's in the middle, right? Okay, and if you're using inverse distance, so now imagine if I have two wells that are twinned, okay, side by side, they both have 10, all right? Then if I go into inverse distance, it will tell me that the data value in the middle is going to be 7.5. Okay, it's going to weigh on the high end because there are two wells side by side. Okay, when in reality, we all know the wells are side by side, so that shouldn't impact the value in the middle, right? And kriging takes that into consideration. So it looks at two wells that are a data set that's really close, and it says, yeah, but, that's one value. And so it will tend to give you a more unbiased result.
in cribbing, there is an element of subjectivity to that because you're trying to match variant around.
Sure.
And that's an opinion. I mean, it's not, it's what
Sure.
you think is the best fit.
Yep.
So, yeah, I appreciate the answer.
Yeah. And, you can always do conditional simulations as well, where I don't do it very often. I used to do a lot in Algeria, but I don't do it here, where you look at, you can tell it, give me 500 different interpretations of whatever the property porosity. Okay. And you'll get 500 different maps of porosity. Okay. Which go through a statistical range. And then you can look at it and say, okay, what's my average? What's my mode? What's, a 90% probability or all that kind of stuff. So but there is a little bit of art that goes into it. And you're not, as a geologist doing this, you're not a monkey on a string. I mean, you can impose reasonable, reasonable persuasion in the model to give you results that make sense.
We've had another question too about software, I guess, but Tom Hampton has commented he's seen open source simulation software available, which will help model secondary recovery and will help drive the need for 3D models. Could you comment on the cost of 3D software and the availability of open source tools out there?
Oh, yeah. So that's a good question. So there is GeoLib, which is open source software. And I just haven't used it. So I am sort of staying with the stuff that's really designed for oil and gas kind of stuff. But GeoLib's a good thing to look into. And modeling costs are, the actual software cost is pretty high. It's like any other oil field software. But that's one of the reasons I like Joule. So they'll make exceptions for small guys like me. So like right now, originally, I'll just say, I'll give you the numbers. So like originally I paid $80,000 for the software. And to keep up with it and have support, I pay about 16 every year. Okay. But if I wanted to, I could make that like, and they do that by quarterly payment, right? So you could do that instead of owning the software. For me, I own the software, so it's the license. But you could go in and do a monthly, sort of a rental type thing, right? And have software and support for not such a big hit up front. However, if you're any kind of oil company, I will just point out that the cost of getting the software is oftentimes less than the cost of hauling the trash off of the site after you drill. Okay, so it's just, we look at things and say, oh my God, that's a lot of money. And it is, but if you're making decisions off of that, it's a pittance of a cost. And a sort of a small plug, but recognizing that. So one of the things that I do is like, certainly I will give my services, anybody that, has a project, thinks it's interesting, great, we can work together on it. If you have a company and you want to get the software, that's cool. And I'm happy to help. So I'm happy to give some advice and sort of counseling along the way, get people over rough spots. So sort of a user community here in the States. So yeah, just get in contact with me. If you have any comments or questions or anything, just feel free. Give me I think my email is on the slides. So just get a hold of me.
Any other questions? We're at the end of our time anyway. Thank you so much.
Sure. Thank you. Appreciate it.
Like I said, I will email or I will real mail. Sorry, your thank you gift.
Ooh. Okay.
Walked out without it.
You mix that first structure, that Oklahoma structure.